Okay, so we start to move on to study lecture 2 in section 4. So by now we understand that the three major pillar or three major device inside Internet of Things include microcontroller, sensor, actuator, all right? And the robot is a mini version of IoT because inside a robot, we have a networked sensor, we have a networked actuator, all right, on top of the link, join, etc. And also inside automation system, we have a control system, and each control system must have an actuator and a sensor. So therefore, in the production line, we could imagine there are presence of many IoT, all right? And for IoT, we know with the use of a microcontroller, we should be able to build up a network for data communication, all right? Why do we need to have a data communication? The answer is what? Each node could be a data collector, and each node could be execution or executor or an effector, which will add a coding to control signal. All right. So therefore, IoT could be considered as a distributed sensor or distributed actuator. Right. So then it is very important for us not only to know what is a microcontroller, but also for us to know, okay, how to interface with the sensor, how to interface with the actuator, right? So in lecture 1, we know that among all the sensor, basically we can categorize them into two types. One belong to analog sensor, another belong to digital sensor, all right? Then for analog sensor, our strategy is to convert the value of a physical quantity on the measurement into voltage, all right? Why into voltage? The reason is microcontroller by default is a sensor for the measurement of a voltage, right? So that is for analog sensor. So in lecture 2, we will study the detail, okay, of doing interface, okay, with analog sensor, or how to convert or transform analog sensor into networked analog sensor or networked sensor, all right? So that is the purpose of doing the study of lecture 2. Then in lecture 3, we will talk about how to transform a digital sensor into networked sensor, all right? So if we are able to interface with these two type of two category of sensor, that means you are ready to build up IoT with a sensor, right? Okay, I guess all of you have my lecture slide, like this is a soft copy of my lecture slide for lecture 2. And you see they are close to 100 pages now, right? Or over 100 pages, right? Then you may ask this question, how come so many content for this lecture 2? The answer is we have a very cheap microcontroller with a lot of capability for us to handle all kinds of requirements, not only in Internet of Things, but also in manufacturing, in other domain, all right? And if I make a comparison or do a little bit analogy, okay, make an analogy between microcontroller and the vehicle. So actually, it looks like you pay a price of a bicycle and you get a sport car, okay? You just think this situation, you pay a price of a bicycle. You say, you go to a shop, you say, I just want to buy a bicycle because for me, I just want to travel from my hostel room to the lecture theater, all right, inside my campus. Okay, anyway, no point for me to drive a sport car inside my campus, all right? But the shop offer you, with the same price of a bicycle, give you a sport car. All right. So once you have a sport car in hand, does not mean you should consider your campus like a racing circuit, right? You drive your sport car like a racing car. Otherwise, you feel, okay, it's very difficult to drive a sport car. For this case, it's the same. All right. To interface with a single analog sensor is extremely simple. All right. But with such a low-cost microcontroller, the vendor give you, it looks like a super microcontroller, right? So it's like you get the sport car. Actually, you just need to have a bicycle. So that creates complexity. You say, I just want to ride a bicycle. How come I need to learn how to drive a sport car? Okay, so you may have the same feeling, but as long as you know this situation, it's easier for you to adjust your mindset as a user. You can drive your car at 1 kilometer per hour, yes or no? Also, your car can drive at 200 kilometer per hour. It does not mean you have to drive your car at 200 kilometer per hour. You still can drive your car at 1 kilometer per hour, all right? Keep this in mind, okay? You see a lot of configuration, a lot of possibility. It's like inside your sport car, a lot of button, a lot of switch there, but you don't touch them, right? You just play the minimum one of acceleration, drive at 1 kilometer per hour, like a speed of a bicycle, let's say, then steering wheel, like a steering wheel of a bicycle, done already, all right? Then you feel comfortable, okay? So this is why, because this lecture, I just cover all the possibility. For those of you, maybe a few years later, you want to know what is the maximum capability of this microcontroller, then you still remember, all right? All the information are here, all right? So, okay, prepare yourself, okay, for the study of this lecture 2. So it's like drive a sport car like a bicycle, understand? And you face a sport car, then try not to be afraid. Wow, there are so many things inside the sport car, but use it as a bicycle, done already, all right? Okay, so, and then we move on, okay? And here I just quickly remind you, okay, actually, in order to have a network the sensor, actually you just to have a network the system. And I believe last week we have already studied the basics about the network system, all right? Then I will just highlight to you these two important building block for us to do the conversion between digital number into analog number into digital number, all right? So just in principle, okay, you know this possibility. After that, you will see to do conversion from digital value to analog value is easier, cheaper, faster, okay? Therefore, our requirement is to do conversion from analog value into digital one. Then we can leverage on this cheaper device of doing digital to analog conversion to obtain the result of doing analog to digital conversion, because this is a popular solution, very cheap solution, which has been implemented by all the microcontrollers. And now you understand why all the microcontrollers are so cheap, right? It's like you are paying a price of a bicycle, but you get a sport car, right? But you must consider this as an advantage. Like you should not say, this is a drawback, it's a headache to you, all right? Actually, it's not headache. Like you can drive a sport car like a bicycle. Like it's not a problem. All right. So put yourself, adjust your mindset with this thinking. Then you will feel comfortable. Otherwise, you will get lost. All right. because you say, I just need a bicycle, and then you show me a sport car, and then you get lost, right? Okay, so you can drive a sport car like a bicycle. It's no problem, all right? Okay, so then how to build up a network system with an analog sensor. So in this case, you must think in the context of robot, think in the context of automation system. So inside the robot, all the motion must be under control. Then we have a feedback control loop. Inside any automation system, we have a control system, and the inside control system, we have a sensory feedback. Okay, then we try to look at the way how to interface a sensor with a controller. Then immediately you know that there's a conversion between analog value into digital one. For example, this is like a chemical manufacturing. This is the typical scenario of a chemical manufacturing. We may want to know what is a sensory feedback, right? To monitor the level, the flow rate. So this video we are showing you the requirement of making use of an analog sensor. Okay, this video has no voice, all right? Okay, so you can see, okay, so you have a storage tank, okay, which stores the intermediate product, because chemical manufacturing, all the products are more or less in the form of a liquid. So these are the product in the form of a liquid, all right? Okay. Then we can talk about the level of a liquid, the pressure inside the tank, all right? So then we have a sensor, but the news to you is all these kinds of a sensor are analog sensor, all right? So immediately, if you have a server inside your production line, then your server usually is a digital system, then how to interface digital server with analog sensor, all right? Okay, so you see all these requirements. And here is one more video. And this also is a kind of looks like a chemical manufacturing plant.
Most of the chemical process industries, the manufacturing process is continuous. There will be many operating parameters that change continuously, every fraction of a second. These operating parameters are often called as tags. Plant operators monitor and control the process conditions through process control systems like DCS, SCADA, PLC, etc. The process team monitors the plant operation and performance by calculations and data analysis. Process teams identify the constraints and troubleshoots the plant problems. Process monitoring and analysis is essential for continuous improvement of plant performance. The performance calculations need real-time and historical process data. The performance calculations are also done manually, repeatedly on regular basis. The process team often sit outside the control room, and they struggle to get these data manually. Further, the historical data is limited to few days, due to limitations in process control systems. The process monitoring becomes easy and efficient with INSYS InfoView. The process data are collected from process control systems and stored in INSYS server. The performance calculations and KPIs are evaluated automatically. InfoView provides analytical tools for converting the process data to information and to visualize it. These information is then made available across the organization and across devices.
Okay, this should be good enough already. So from the video you see, okay, in the chemical manufacturing plant, we need to use analog sensor to collect the plant data. Why to collect the plant data? Answer is we need to have information display. The information display is for the manager to make a decision to monitor the operation of a chemical plant, all right? So then you see there's a requirement for us to do interface with analog sensor, right? So then what is a network system? I guess this is just a review about this definition. So we have a system. System means what? System consists of an interconnected action element, interacting element or entity, all right? And one way to do the interconnection among all the entity is to make use of a network, right? So interconnect, make use of a network to achieve such an interconnection, all right? And the robot is a mini version of IoT. And here you see you have a 1, 2, 3, 4, 5 mobile robot. Each mobile robot has a mobile base plus arm manipulator. So you see each robot actually could be considered as a mini version of IoT, all right? And then for any network system, okay, we have an input, we have an output. Output is a response. Then we have an inner process which will transform the input into the output. All right. Even for mobile manipulation guided by vision. So you see, we have a camera, we have an arm, we have a mobile base. Then vision. You see, vision is a sensor. All right. See the environment, all right, get the input, then the robot has a brain to make a decision, then output motion, right? So this is a typical scenario for you to see a mini version of a networked system, all right? So, and last week I also mentioned that the best system in the universe should be static system, but the bad news is in the universe, most systems are dynamic system. Then we need to transform dynamic system into static system as much as we can, all right? By default, all the dynamic systems are in the open loop mode, all right? Then the solution for us to convert dynamic system into system which are very close to static system is to close the loop or make use of a feedback control loop is this one, all right? So with the use of a closed loop control, we are able to transform the dynamic system into a system which is close to a static system, all right? Because static systems are the best system, all right? So we want to have a better dynamic system. How to make a dynamic system to be better, all right? Just to make land to behave like a static system as much as we can, right? So once we close the loop, immediately you know the interface or interconnection, right? First is an interconnection between sensor and the controller. Second one is an interconnection between controller and the system under control, all right? And if sensor is analog, if the system under control is analog, therefore we need to do the conversion, right? Okay, because output, digital output from controller must be converted into analog input into analog system, because analog system can only take in analog value. So you see, okay, if the sensor output is analog, then we need to convert analog output from the sensor to become a digital input to controller. So now you see these two devices, AD converter, DA converter, all right? So these are very, very important devices inside a networking system, all right? Okay, then this video showing you, right, the complexity in the input, complexity in the output in the robot system or in the automation system, because inside this video you see a robot, you see a production line, all right? So actually that gives you an idea about the automation system, robot system, control system. Control system means it's a control loop inside the robotic arm, right? And on top of that, you see the conveyor. Conveyor is also an automated system, right? So that gives you idea about the relationship among the robotics, automation, and the IoT, all right? So then in general, today, all right, the machine's brain are based on the use of microprocessor, digital computer, or microcontroller. So microcontroller are digital system in nature. So microcontroller can only output digital number, can only take in digital number, all right? So this is why we need to have a DA converter, AD converter to interface with analog system, analog sensor. So this is very, very important. All right. So this is just a small exercise for you to play. Okay. If let's say we have a machine brain, okay, then what are the possible type of analog input? Visual one, lighting is a visual one. Auditory one is acoustic sensor. Motion one, so it could be position sensor, right? Okay, or force torque sensor, because force torque are also related to motion, right? Then for acoustic sensor, okay, we have a microphone channel. Actually, microphone is analog sensor because output from microphone is analog signal. So this is why we also need to do the AD conversion. All right, okay. Then how about output? So let's say our digital system can output analog value as well. So the speaker actually in your computer is an analog device, and to emit the lighting, your keyboard can emit the light, also analog signal, and to display, okay, the screen actually is an analog system because it emits the light display. Okay, so these are the typical example, right? So then how to play back the recorded voice and music. So we use a speaker. So speaker, you see, is a typical analog device. All right. So therefore, in order to construct all these network in the system, which involve microcontroller, actuator, sensor, then we need to have these two special type of device, DA conversion, AD conversion. All right. So we start with the DA conversion. This is just for you to know. DA conversion actually is very simple, very cheap. All right. Then we can leverage on this device to build to design AD converter. All right. So why you need to know a little bit of this one. Okay. So working principle is very simple. Input is a digital number, output is analog number. All right. And the simple solution is this diagram. For those of you, if you have studied year 1 physics, I guess you know this circuit. All right. So input, we have a network of resistor. The output is a single voltage. Actually, you can consider this if you, okay, it's very important for you to know this terminology. MIMO, MISO, and SISO. So MI means a multiple input, SI means a single input, MO means a multiple output, SO means a single output. Also, these are very simple terms, but it is very, very important for you to find the solution. Because without these simple things, if you start to directly play with MIMO, you will waste a lot of time, you will waste a lot of resources. And today, for a lot of research in the area of doing deep learning neural network, actually they are doing the tuning of MIMO, all right? If you have a knowledge about the control theory or this concept of MIMO, SISO, automatically you will get this conclusion, okay, is wasting people's time and the resources to play with MIMO, right? So we will try always to convert MIMO into MISO or SISO. So this is an example of MI. You have a multiple input because each bit is an input, V1, V2, V3, and single output VO, right? Okay, then you can easily derive this equation. Input is a function of output. Immediately you understand output is a function of the value of the bit 0, bit 1, bit 2. Bit 0, when you take a 0, means 0 watt. If it's 1, means 5 watt. That means V1 equal to 5 watt or 0 watt. V2 equal to 5 watt or 0 watt. V3 equal to 5 watt or 0 watt. All right, okay. Then how about the AB in general? Because for this design, it's very expensive. You see, we have R, resistor with R, resistor with 2R, resistor with 4R. If we increase the number of bit, then we have many resistor with a different value. But if we mass produce such a device, it will be very expensive. So it is always try to reduce the number of type of a resistor. Now you see this network, right? We only have 2R and R, right? And this also is a MISO, multiple input, single output, all right? And good news to you is this MISO actually is equal to the sum of SISO, single input, single output, all right? So it means we just consider we have B0 as an input, V as an output, then B1, B2, B3, B4, B5, B6, B7 equal to 0. Then we have another SISO. B1 is input, V is output, all the rest are 0. Then have another SISO. B2 is input, V is output, the rest are 0. All right. Then for each SISO, actually is extremely simple. All right. For example, if you only have a B0 as an input, B1, B7 are 0. Because B7 are 0, then 2R is in parallel channel. Because look at the operational amplifier, another input connect to the ground. So it's equivalent, both input are to the ground, 0, right? So the 2R connect in parallel become R. Then R plus R become a 2R. Then this 2R is connected in parallel with a 2R of a pin 6. Then it become R. This R plus R become 2R. This 2R is connected in parallel with 2R from the pin B5. Then 2R become 1R. So you see, you can simplify it is equivalent. If you're looking from a B0, the total resistance is what? Is 2R plus R. That's it. All right. Then the voltage, all right, at this point, voltage at this point from B0 should be 1/3 of voltage at the B0, because this is 2R. Then the rest here, you lump them together is equal to R. Then it's 1/3. This is why you see V0 times 3. Now you look at this voltage. What will be the voltage? If let's say you have a voltage here, then what will be the voltage here? Because all the rest of a network of a resistor is equal to R, that means what is a half. So then is this one divided by 1/2. Once you have a voltage here, this voltage first divide by 2, you will get the voltage here. Another divide by another 2, you get the voltage here. By another 2, you get the voltage here. All the way you reach the voltage here. Then you can say, what is the voltage belong from B0, which will contribute to the voltage at the input here? Answer is what? 1/3 of a voltage at the B0 divided by 1, 2, 3, 4, 5, 6, 7, divided by 7, 2. All right. Because 1R you divide by 2, second R divide by another 2, third R divide by another 2. So this is why is 1 divided by 7, 2. All right. Then for B1 here is the same. What will be the voltage here is 1/3. Then 1/3 of the voltage here, what will be the contribution to here? Then you will divide. You just count the number of R. 1, 2, 3, 4, 5, 6. Divide by 6, 2. This is why you get the divide by 6, 2. Okay, then you get this equation very simple. All right. So, okay. So it's interesting. Then for analog to digital to analog conversion, these are the terminology. All right. We need to look at the output range, input range, because the output is a voltage, input is a digital number. Then we need to count the number of a bit. Right. Okay, then output range, maximum value, minimum value. Then we can talk about the digital resolution. That means how many voltage per unit bit. That is a digital resolution. Analog resolution means how many bit per unit voltage. All right. So let's show us the sensitivity. Okay, when 1 bit change, how many voltage will change? All right. Or when you change 1 watt, then how many number of a bit will change? All right. Let's show you the sensitivity. All right. Between input output variation. All right. Okay, that's it. Then this is a small exercise for you to do as a homework. Then you test your understanding by yourself. All right. Then how to do analog to digital conversion? Because here we have analog sensor, we need to convert into digital number, all right? So then how to do it, okay? So this video show you entire process, right? First is jumping, we call it a jumping, because it's a time function. Then this is a quantization, all right? Just 2 steps, jumping, quantization, that's it. Then we get the digital number, all right? Very simple, all right? And one more video.
Analog to digital converter is a device whose input is in analog form and output is in digital form.
Jumping, quantization, encoding or not is secondary.
Second is quantization, third is binary encoding. Analog to digital converter, ADC. Analog quantity may be voltage, temperature, sound, speed, audio, etc. It is information or signal. Digital means it is in binary form, 1 and 0. 1 means on and 0 means off. Converter is a device. Analog to digital converter, ADC, is used for converting analog signal into digital form. Most of the data is in analog form, but most data processing is done using digital computers. So for processing and / or modifying signals, we need to convert it in digital form. Pulse code modulation, PCM, technique method is used to digitally represent discrete analog signal. PCM consists of 3 stages. 1 is sampling, second is quantization, and third is binary encoding. The sampling measures the amplitude of the signal at different interval. Quantization is the process of converting the sampled continuous large set of input value to small countable discrete value. Binary encoding is assigning a binary equivalent to each state of output. There are 4 types of ADC. 1 is counter type, second is integrating or dual scope, third is parallel or flash, fourth is successive approximation. Examples of analog to digital, A to D, converters are microphone, converts analog audio signal to digital form, voltmeter, converts analog voltage signal into digital, scanner and camera, converts analog image into digital form, digital speedometer, converts analog speed into digital form, etc.
Okay, so actually the working principle is very simple. It's like a jumping, quantization. So we have analog as an input, but you must pay attention. Analog is not the a value always there. It's a fixed value because it's a value is changed with respect to time. All right. How to capture this, adapt to the time variation. So the this operation must finish within short period of time. So therefore, you can easily follow the variation of analog input. All right, keep this in mind. All right, theoretically, it's very simple. Jumping, quantization, done already. So if I make an analogy, compare it with a bicycle. So to do this is like a bicycle. To ride the bicycle is very simple. You have a pedal to produce a velocity. Then you have a steering handle to change to control the direction. Same, all right? But the thing is, when you are going to buy a bicycle, when you are going to buy a AD converter, microcontroller with AD conversion, all right? And with the price of a bicycle, you get the sport car, all right? With the price of a book, small book, you get the super microcontroller. That is the situation. That makes your learning slightly complicated. You get lost, all right? But you stick to this mindset that I'm just driving it as a bicycle. I don't care whether it's a sport car or super car. I just consider it, this is a bicycle to me. That's it, all right? It's the same. When you get the super microcontroller, you just think, I just need to do jumping, quantization, I have a single input, finish, all right? The rest function, I don't care. I do not need them at all, all right? Then your life is easier, very simple. Jumping, quantization, done already, all right? Okay, so this is the working principle of ADC. And in the video, I already explained to you. Then what is jumping? Because this is a time function. Then it's not the, because the time function, continuous time is infinity, you have infinity number of a continuous time. But we just do have a discrete time now. Let's say every 1 millisecond, I do everything, right? It should be good enough, John, right? So every 1 millisecond or every second, depends on the application, right? So that means to convert continuous time into discrete time. This is called as a jumping, all right? Okay, I only do the measurement at the discrete time, not continuous time, all right? So take a jumper. So okay, once you get the jumper, but this is the analog value at this time, then I need to convert it into digital number. That is called quantization. That's it, very simple, all right? So then quantization is at this time, I may get this analog value. Then I do not use this value. I use a very close digital number to represent it. If the closed one is 100, all right, then use 100 to represent this value, all right? And in this case, if the closed one, close digital number to this value, analog value is 111, then I use 111 to represent it, all right? So then depends on the number of the bit, because quantization, there's an important parameter here, is how many bit to represent all the possible number of digital value. If you use a 3-bit, the possible number of digital value are A. Why A? You can easily count because you only have a 3-digit, then you have this binary number 000, smallest one, or 111. Then in between is 001, 010, 011, 100, 101, 110. You count the number of a value, possible value, 1, 2, 3, 4, 5, 6, 7, 8, 8. All right. So A equal to 2 raised to the power 3. So this means I only have a 3-digit for binary number. Okay. Each digit is 01. I have a 3-digit to represent a binary number. Each digit can only take a 2 value, 01. So 2 raised to the power 3. 3 is a number of a digit. If I have a binary number with a 16 digit, is a 0000, I have a 16, all right? Each digit can take a 2 value, 01. Then the total number of digital output is 65,536, all right? It's a lot, all right? Okay, so it's good enough. Then what should be the design solution for ADC? ADC actually, you see, make use of a DAC because for a computer, it's easier for us to predict all the possible number because it's easier to predict all this value. I can always predict from 001, 000, 001, 010. It's very fast. I predict. For each prediction, I do a comparison because for each prediction, I can produce, do the DA conversion to get the analog value. It's like here, let's say, how do I know this guy is 100? First, I predict it is 000. I get the analog value. I do a comparison. It's a big gap. Then I do second prediction, 001. Then this analog value is very much different from this one. I predict next one, 010. Then I get the analog value. You see, is far away, right? Then I do third prediction, 011. Again, I get the prediction conversion, a DA conversion, get this analog value. I do a comparison. You see, big gap. Then I did another prediction, 100. Then done already. You see, predict. I do DA conversion, analog value. Predict the value with the real value is very close, done already, all right? So now you see, this is once you predict digital output, immediately convert into analog value. This predict analog value compare with the input analog value, all right? When is close over match, then it will output a signal here. There's a transition. Let's stop the prediction, done already. All right. Since the microcontroller can do prediction very fast, 1 million per second. 1 million per second is a lot, John. All right. And instantly you get the analog value. Then you do the comparison. So that means actually give you the feeling is instantly you get the right prediction because 1 million prediction per second is a huge amount of prediction. All right. So give you impression. Once you have an analog input, instantly you get the right prediction. All right. Okay. So this is the working principle, very simple, all right? So this is why microcontroller is so cheap, right? Okay. Then application in the video, besides temperature, humidity, many other physical quantity are analog in nature. For example, acoustic signal actually is analog signal. Now you see how to get the digital number, jumping, then quantization, and then you will see how many jumper. Let's just give you an idea, 8,000 jumper per second. All right. Okay, so you have 8,000 reading. Then for each jumper, we use 1 byte. Okay, we use a bit is 1 byte to represent it. Then how many byte? What is the data size? You see 1 byte, that means 8,000 byte. Okay, or in terms of a bit, so it's a 64 kilobit per second. So it's a lot of data, right? Okay. Then how about vision system? So this is a very small vision system. It's a 2 by 2. So 2 row, each row, because this 4 unit is a single color pixel, RGB pixel. So it's a red, green, blue, RGB. This is another pixel. So in total, we have a 4 pixel, okay? So it's 2 by 2. And in practice, you may have more than that. If you look at your camera, it's a 10 megapixel, right? It's a lot. Then this is a 100 by 100. You see, when we read out the signal, is a row by row, then column by column to ship out. So actually, so this is again, you use this concept like MISO, multiple input channel. So you have a matrix of 2 by 2, all right? Single output, okay? So how to get this MISO, so basically it's a ship row by row, then ship out the column by column. Then you get the time function as a single output. So then this is a single output as a time function. Then first thing to do is what? Jumping to create, make a time to become discrete. Then at each discrete time, convert the analog value into digital number, quantization, done already, all right? So then this is a high resolution camera, is 100 by 100. Then instead of one ADC, you see, we must use multiple ADC. Then this is an example of MISMO channel. Because this is a multiple input, you see, you have a multiple ADC, so multiple output. So it's MIMO system, all right? So it's very important because not many people use this term, MIMO, MISO, SISO. But actually, this term help you to understand the nature of a signal flow inside complex system. All right. Then similarly, have some specification, sensitivity between input output. This is quite easier for you to read. Okay. This is more exercise for you to play. Okay. This also gives you indication for ARM Cortex microcontroller. Actually, is by default is a sensor which measure voltage, and the range of an input is fixed. It's not like other microcontroller. They allow you to program the range. This one is fixed, always 0, 3.3. If your sensor does not output the voltage in this range, you can always design a small circuit, either to scale up or scale down into this range. So that is not the issue. To scale up, scale down, analog voltage, you just use a network of resistor done already, quite straightforward, right? It's not the issue. Okay, now you have this Cortex M4 microcontroller, low cost, all right? So with the same microcontroller, you can build up a 2-dimensional network, you can build up a 3-dimensional network, and also you can directly connect your analog sensor to it to have a network in the sensor, all right? So you see, with the study of a single microcontroller, actually, you know everything already. You are able to implement not only a network for communication, you are also able to implement network for sensor and also a network for actuator, all right? So this is a very, very good hardware for you to understand. Another good news is with the price of a bicycle, you get a sport car, all right? So it's the same. With the price of a book, okay, very cheap, you get a super microcontroller, right? Why is a super microcontroller? You see, with a single microcontroller, you can interface 12 sensor, because it's like I only need to know how to convert one sensor, right? Connect to one sensor. But this hardware like allow you to 12, right? And with one sensor, I just need to have a single device to do jumping. Now you see he give you A, right? This A divided into 2 groups. Each group has a 4. And for quantization, you may say, I just need to have a 1, all right? But he give you 2. Okay, now you understand? With the price of a bicycle, you get the sport car. But you should not complain, all right? Wow, make my life so difficult because I only know how to ride a bicycle. I do not know how to drive a sport car. But actually, you can drive a sport car slowly, 1 kilometer per hour. All right, it's not the issue. Okay, keep this in mind. All right, complexity is due to this is a sport car. Also, you just want to use a bicycle, right? Okay, then why use this microcontroller? The beauty is this one not only support network of communication, it also support networked sensor, networked microcontroller. All right, that's it. All right, and then what is your role? You just put yourself as a role of a user, right? Also, just not mention, you just want to be a user of a bicycle, but you get you have to behave like a user of a sport car, right? Because you pay the same price, but you get the sport car, right? Okay, so that's it, right? And okay, if you want to know more about the microcontroller, then you need to study all these topics. But here, the benefit to this course is I give you a few lectures. Actually, you more or less know the capability of this microcontroller, right? So you have a software, you have a hardware, how to interface input. Interface is to interface with the sensor, output. Next week, we'll study output to interface with the actuator, right? And as a user, the good news is it's like as a driver of a car, you just need to know how to turn the steering wheel, how to push the acceleration pedal, how to push the braking pedal, how to brake your car, how to accelerate your car, how to turn left, turn right your car. That's it. You don't need to know how to design the engine, all right? Okay, so to use a microcontroller is similar like that. You just need to know how to set the register to configure it, okay? For example, you just tell I only have a 1 sensor, not 12 sensor, right, etc. And then how to configure all these register? You just use one of these 2, 3 instruction. Don't need to use 3, just one of them. Done already, right? So that's it, right? It's like when you drive your car, you need to know I just drive at 1 kilometer per hour, like a bicycle. That's it, right? Okay, so it's not a big issue, all right? So then this one highlighted the feature, just summarize. You see, you can have 12 sensor, okay? And that each digital value is encoded with a 12 bit. That means you may have 4,096 possible value as an output, digital value as an output, all right? So you may have a 12 sensor at the input. They give you 2 device for quantization. They give you A device for jumping. Where is the A? I do not know. Okay, maybe next slide. Okay, they give you A. Here. Each quantization unit here, each have a 4 programmable jumping conversions, but they use this term sequencer, jumper sequencer. Jumper sequencer basically is a quantization device, okay, or quantizing device. All right, I use this term, maybe it's easier, but this is the name given by the designer, but you should not ask this question, why? Why give this name? All right, so conceptually, basically it's doing quantization device. So you have, okay, for jumping device, you this is a jumping device. Jumping device, ADC here it basically means it's a quantization device. So you have a 2 quantization device, A jumping device, and 12 input, right? So, and all this number does not match. 12 input, A jumping device, two quantization device. That confuse you, right? It's like when you buy a sport car. Sometimes you see you have a lot of switch there, all right? Okay, then you get confused. You say, I just want to go from point A to point B. A lot of things I don't care, right? How come so many things there, right? Okay, something like that. Okay, now this give you some idea about the hardware aspect. Okay, 12 sensors input, 2 quantization device, but here did not show you, but inside here, around this area, you have a sampling device. All right, and this slide help you to understand. Okay, so then because the number does not match, also they give you flexibility. Any sensor could connect to any sampling device. Like make it create another headache to you, China. It's not like I only have one sensor by default connect to this sampling device, by default connect to this quantization device. I don't care about the connectivity, right? But this guy is like a sport car. you say I only want to drive ride a bicycle, but you give me a sport car. Sport car allow you to configure a lot of things. Like it's like your engine could be configured at a very, very powerful mode. Powerful mode means what? You can accelerate in very short period of time, but waste a lot of fuel. Okay, and you can also configure your engine like economic mode. You will minimize the fuel consumption, but okay, you cannot accelerate very fast. Like something like that. They give you the flexibility to do a lot of configuration. Here is the same. Any sensor could be connected to any sampling device, any quantization device. Then you see, you need to configure that. Okay, that kind of flexibility is called by the multiplexer. Multiplexer is like a switch. It's a switch for you to say, or switch input number 1 to output number 10 or output number 6, something like that. All right, multiplex is doing this. Okay, switch input number 3 to output number 5. Understand? Not like that. Okay, and the output, they also give you the buffer because your CPU may not fast enough to read out the data, then temporarily store inside the buffer. And they give you another possibility, because this is needed for people doing quality control in the manufacturing, but this is beyond most of you. For those of you, if you are working in the manufacturing industry, you may understand what is a process control, what is a quality control. Quality control, you set the value, what is the upper limit, lower limit. For example, upper limit for temperature, lower limit for temperature. If let's say you do a production and the temperature is very critical, temperature can only vary between, for example, 25 to 20 degrees. So upper limit 25, lower limit 20. Beyond that, you must send alarm, all right? Something accident, etc. So then he give hardware support for you to do that. This is why you have a comparator. So this value go inside the comparator, because each comparator will have a 2 limit value, upper limit, lower limit. Hardware will do the comparison. If beyond that limit, it will send out the internal signal. Let's say it's like when you drive a bicycle, you don't care about how to tune the engine. But once you get the sport car, people may ask you how to tune how to configure the engine. Then you say headache because I only want to drive a bicycle, all right? Bicycle don't need an engine, but the sport car want you to do that, all right? Okay, so that is this situation, okay? With the price of a bicycle, you get the sport car. That's it, but you must consider this as an advantage. Don't complain, all right? So ARM microcontroller is very powerful one, but very cheap, right? Okay, so this, okay, another thing is, since you have a 2 quantization device, they allow you to offset. That means they do not start at the same time. They have offset. Offset means, in terms of electronic language, means it has a degree difference, as a phase shift. So this allow you to make these 2 quantization, taking input from the same sensor, then to double the resolution. For example, for this one, the maximum resolution for sampling device is 1 million per second. If we create phase shift of 180 degree, then we can double, then we can have 2 million jump data, okay, per second, because we just offset by 180 degree, all right? But the both of them taking the same input, okay? So this is this application. But if you drive a bicycle, you can ignore this one. Does not matter, all right? Then from here you see there are so many register for you to configure, but only the flow of data is here. Input, you have a 12, then flow through. Here you have a sampling device. Here you have a 2. Then either go to the buffer FIFO or go to digital comparator. Then before you can read out. All right. So it's like you get the sport car. You just imagine your sport car is a bicycle. Then your life is easier. All right. You say I only have one sensor, then one sampling device, one quantization device, and one location to read the data. I don't care about the digital comparator. Done already. That is very simple, right? You just imagine your sport car as a bicycle. Done already, right? It's very simple, right? Then this one help you to how to do the physical connection. So you see Y12 sensor. You see all these are the input for sensor. Sensor number 0, sensor number 11, and physically you must do the connection. Okay, what is the pin number of IC chip? So pin number 6, 7, etc. IC chip, I guess later I will show you a photo of IC chip. All right. Okay, so this is IC chip pin number, and the IC chip pin number has a name for the pin of the port. Port is a 1 byte. PE means the port of port E. This is the port D. And port B. So you see, since we only have a 12 sensor, so we will not make use of all the port pin. And here you may ask this question, why jump port E, port D, and the port B? Don't ask this question why. This is a designer's decision. It's like when you buy a car, don't ask question why is the design of a car in that way. You just use it, all right? You understand, and you just use it, all right? Okay, so, and this register will tell you for your microcontroller, actually, do you have the digital comparator or not? Actually, what should be the number of a sensor you can take in? Okay, but this is because some buyer may ask the vendor to remove certain hardware. It's like, really, I do not want to have a sport car. Also, is the price of a bicycle. Just give me a bicycle. Is this situation? Then the vendor will customize. Then if you buy a second hand of Cortex microcontroller, you need to do this verification. You may get the second hand of a microcontroller with reduced capability. Okay, this is just something for you to know. All right, if you buy a second-hand car, and this car may be modified version, all right, not the standard car. Okay, by default, you have a 12 input, you have a sampling device, you have a 2 quantization device, all right, okay, but you may purchase a second-hand vehicle, but has a reduced capability, all right, so you can use that register to verify. Okay, for input range, this tell you input to this microcontroller. If you use it as a sensor, must be voltage, right? Within this range, 0 to 3.3, okay? And this showing you inside, and actually the hardware is very robust because he will do some filtering. So even in the noisy environment, if it's not exactly a lot of noise, and this is also very reliable, right? Just for you to know this. And the output is 12-bit, so therefore, you have this input-output relationship. Input is 0 to 3.3, all right? Output is 12-bit. Maximum value of a 12-bit is 12,111, all right? And if we do the, okay, you may heard of encoding. We can encode binary number with a hexadecimal format. Hexadecimal format means group 4 binary number into single digit. So 4 binary number, small value is 0, maximum value is 15. 15 is F. We use F to represent 15. 0 to 10, 10, 11 is C, 12 is D, 13 is E, 14 is E, 13 is D. So you have a B, 10 is A. Okay, 0 to 9, 10 is A, 11 is B, 12 is C, and 13 is D, 14 is E, 15 is F, right? So then because we have a 3 group of 4 digit, so this is why you only have a 3 digit in the format of a hexadecimal. So it's a FFF is a maximum number. So small number is 000 all the way FFF. So then you have this straight line. It's quite straightforward. So this is a homework. You do exercise, verify this result is correct. All right. Okay. Then how to operate this super microcontroller? It's like your intention is just to ride a bicycle, but you with the price of a bicycle, you get the super car or sport car. Now the headache to you is how to configure this super car so that you can drive it as a bicycle. That is this situation, right? So since you get the sport car, then no choice, you must know a little bit how to configure, but always think in a simpler way, right? First, you must tell the hardware, because you can have a 12 sensor. If you connect one sensor to one of these pin, once you do the connection, if let's say you choose the pin of the port E, then here you must find the port E, have a list address. Then in this address, what is the corresponding pin port E? Let's say pin 2 of the port E. Attach your sensor. Then this control the pin 2. You must set this bit to be 1. Just tell the hardware, okay, where are the sensor being connected? All right. Since you can connect up to 12 sensor, and this is like a sport car, have 6 port. So they give you the possibility to configure all the 6 ports pin, right? So this is why you have so many address here. Each address has at least a register, all right? And for each register, they only control connection or no connection of a pin, because each port has an A pin. So you must tell, if there's no connection, you set the value 0. If there's a connection, set the value 1, 0, 0, etc. That's it, all right? So it's very simple, this one. Okay, this is the, okay, you see this is the chip, right? Then you can identify the chip's pin number with the port pin number. You see, this one is a port F, pin 0, correspond to pin 28 of the IC, of the chip, right? That's it, right? And this one is to, okay, turn on, because this one tell you the selection connection, okay? That means here I attach a sensor, tell the hardware. Now here is you say I want to turn on the AD converter, right? Because it's more or less similar. If let's say you attach a sensor here, then you must turn on the ADC module. Okay, so you must do this, okay? Since you can have 12 sensor and all the port eventually could be involved. This is why you must okay, do the configuration. So it's very easier, all right? But if you have a single sensor, if your sensor is always here, then you set this bit to be 1, then here also this bit to be 1, because I have a sensor connect here. That's it, all right? Then set this bit to be 1, done already, right? Okay, and reference voltage. Okay, this one is for you to add in a little bit of noise instead of in case if there's an environmental noise, you may make your reading jump between 2 values, all right? So you add in the noise, actually eventually will stabilize the output reading, okay? Whether you want to add in noise or not add in noise or not, okay? So you just decide here, okay? Put bit 1 here means for this reference voltage is always 3.3, but add in a little bit of noise, all right, to to compensate environmental noise, etc. Right? So that is this. Okay. Another complication is because if you say I have a single sensor, I have a single sampling device, but this one they give you for sampling device number 0. This guy can hold, I mean temporarily can hold a sample, and this a sample could come from a sensor. Wow, that is give a lot of flexibility for advanced user. Then you must tell sample number 0 come from which sensor. So then you need to use a group of a bit to indicate. Sample number 0, you see multiplex is to select which sensor. Okay, select sensor for sample number 0, select sensor for sample number 1, select sensor for sample number 2, all the way selection of a sensor for sample number 7. All right, and for the sampling device, if we divide into the group, then we always name 0, 1, 2, 3, 0, 1, 2, 3. So actually you have a 2 sample sequencer 0 or sampling device number 0, right? Because you have a 2, because you have 2 group, right? So, but for you, if you don't use it, you just set all 0, okay? Don't care, all right? Okay, something like that. And then this one, for each sampling device, either you can do software by turn on, turn off, or let the hardware to turn on, turn off. Why let the hardware to turn on, turn off? It's because once you turn on your controller, automatically the sensor must turn on, turn off. So therefore, there is an intrinsic hardware synchronization. So this one support this hardware synchronization between actuator and the sensor. So you see, PWM basically means next week we will study this one. PWM is a signal sent out to the motor. So you can use this one to synchronize the sensor. Because once you turn on your actuator, automatically it means you must turn on your sensor, right? And you may also have a comparator. You may have an emergency button. Okay, you want to press a button to by any user to on your motor, on your sensor, right? Something like that. So here then you can select, okay, because each module, each quantization device has a 4 sampling device. Then for each sampling device, what should be the internal hardware signal which will turn on the sampling device, all right? So then you have a 4 selection of each selection for one sampling device. That create complication. But normally, if you drive a bicycle, you see, I don't care this one because I do not need to do any synchronize. Then you can ignore, okay? But it's just good for you to know, okay? But in case if you use a motor to simply synchronize it, and then for ARM Cortex, next week we will know. The motor signal also is like a similar. They give you a sport car when you want to buy a bicycle. They also have a 2 group of motor, and each group, then they also have 4 PWM. Then you want to know for PWM number 3, whether it come from module 0 or module 1. So you must indicate. This is why here you tell, right? So make your configuration slightly complicated, all right? Then internal process, this one is easier. Choose the clock speed. By default, you choose a system clock, right? So it's not a big deal. And okay, this one is for you to know what is you could learn the quantization device. The full speed is 1 second per 1 million sample. Complete the task 1 million conversion per second. So you use this digit to do the selection. If you key in value 1, you do the quantization at this velocity, this speed 125 kilobit per second. If you set this speed to be 7, then you run at the full speed, right? 1 million bit per second. That's it, right? Okay, etc. This one is for you to, because for the jumping device number 0, you have an A jumper. Then you must tell what is the nature of a jumper 0. You see all these 0, 0. What is the property of a jumper 1, property jumper 2, all the way property of a jumper A. The property could be, this is the last data to do the jumping. This could be, instead of sensors direct input, this could be the input, which is the difference between two sensor. Difference. You remember we may have a 12 sensor. 12 sensor could allow you to produce 6 difference. You can pair them, have a 6 pair. Each pair output difference output. So D means a difference output. And this controller has an inbuilt temperature sensor, whether it's a temperature sensor or not. Then this is whether to produce an internal interrupt or not. All right, okay, something like that. So you can read, right? And then this is by software to enable. This is just to enable, because you have a 4 jumping device. Whether for each module you have a 4 jumping device, whether you want to enable all of them or not. So here you must explicitly tell I enable them. Okay, so enable them. So this is for you to okay, to turn on the jumper, the jumping device, etc. Right? And here is to help you to do the priority. You remember we only have 2 quantization module. We have A jumping device. So therefore, then there's a Q, right? Because for 4, okay, you must tell what the priority channel. So priority for jumping device number 0, priority jumping device number 1. But you should not set the same priority. Okay, priority means what? Okay, first to do the quantization. Okay, which one first? Which one is the second? Which one is third, etc. So with the 2B, you can have a 4 value, then you have a priority. Highest priority is 0, right? Then lowest priority is 3, something like that. Okay, you set the priority, right? Highest priority is 0, right? 0. Lowest priority is 3. That's it, right? Okay. So now this one is to specify the phase between these 2 quantization device. And just now I mentioned, if you set the phase which is 180 degrees, then you can double the number of jumper per second. All right. So that's it. But if you do not want to do it, it's okay. Okay, this one is for process control. You can set the upper limit, lower limit, because the output can go to comparator. Comparator have upper limit, lower limit. Then the hardware will trigger alarm. If the actual value exceed upper limit and below lower limit, then hardware will set up alarm. So this is needed in the production line. Then for you, if let's say you don't care about this, then ignore it. Okay. So again, you see, you have a sport car. Also, you want to ride a bicycle. All right. So that is situation. All right. You pay a price of bicycle, you get the sport car. All right. Okay. Then how to generate the interrupt? You see, they give you also a lot of flexibility. Or generate once or always or whatever. All right. Okay. So really, this is like a sport car. All right. Okay. So okay, you can ignore it. But remember, you have such a possibility. One day, if you want to do it, then you can do it. All right. And how to trigger and reset the alarm once you go to upper limit, lower limit. In here is to do the reset, because you have a comparator. Then each comparator can produce interrupt. Then here you can do the reset of interrupt. All right. So reset interrupt 7, comparator 7, comparator 6, comparator 0. That's it, right? Okay. So you see, give you a lot of flexibility. Okay. Then you see which comparator will receive which sensors data is here. You see, each comparator can select output from jumper from the quantization device, right? So then you see, because we have a comparator number 7, you can decide, choose what should be the data that come from which sensor. Okay, so you choose the data come from the jumping device number 0. Remember, jumping device number 0 can hold a jumper. So this a jumper can be stored by one of these digital comparator. So this is a selection. of which of this A jumper from jumping device number 0, right, etc. You see, that means this guy can select, okay, whether inside here will hold the data from this device or not, from this device or not, or something like that. All right. So this is why you see all this, okay, selection digit, right? Okay, and this one is to that's our setting of origin. Okay, it's just to enable, okay, to, because the output, you see, sampling device is here. By default, it will not go to here because this is a more advanced operation. By default, you go to here, feed4. If you want the data from here, go to digital comparator, you must set all this bit, must tell, set all this 11111, means they will go to digital comparator. Otherwise, go to feed4. All right. So something like that. Okay. So then the rest is to start. This by software, you can turn on, okay, the sampling device, okay, because you have two groups, 0, 1, 2, 3 per quantization device, okay, so you have a two such a register, right, something like that, okay. Then output, that is another complication. They allow you to average out the output, produce a single output, and this is do a filtering in a noisy environment. Do the average, then actually you can remove the noise. So you can do average up to 64 value, compute an average, then produce a single output. So this is really like a sport car when you just want to use a bicycle. Then average how many digital number before produce the actual output. You can decide up to 64 digital number, up to 32 or up to 2, or don't do any filtering by computing average number. All right. So this allow you to make use of the hardware capability to do the filtering of a wider noise, right, etc. Okay, the remaining I guess should be similar to the one that you have studied in last week. So because internally they can generate interrupt basically is an internal signal. Internal signal, you can mask them out. Don't let this signal go to the CPU or something like that. All right. So then after that, then you run. Okay. Once you run, is from this data register, you can read out the data from a sampling device number 0. Actually, for each sampling device, you have a data register. You can read their data, but to save the space, I just showing you one. Okay, this is from this address, you will get the data from a sampling device number 0. You have another data register for sampling device number 1, number 2, number 3. All right. Since you have a 2 unit, then actually you have a coder, you have an A data register for you to get the data. All right. The digital number which correspond to the number of a sensor. So actually, if you ride your bicycle, basically what you want to obtain is this number. Read this number, you connect your sensor regularly, you read number from here, done already, right? So, okay, but this one gives you really a lot of possibility. In case you are not fast enough to read the number, because for the data come from sampling device number 0, if you go to buffer, they just store there. Then you can take your time to read them out. They also give you indication, index of the head of the buffer, index of the tail of the buffer. Okay, in this register, you know all this. Then you can play. You can know, where to read out the data. That means all the data from the sensor temporarily is stored inside the buffer. In case if your CPU not fast enough to read out the data, right? They will temporarily store inside here, right? So it really is very, very powerful, right? Okay, so then the hardware will also tell you once conversion has been complete, they will generate interrupt signal. So actually your program can just wait. If this bit has been set to be 1, then you just read out the data, set to be 1, read out the data, done already, right? Okay, so it's quite, then how to clear, always remember once you make use of an interrupt to synchronize your operation, always remember to clear interrupt. All right. So last week I already tell you, without the clearing interrupt, you may have a consequence. Right. get some error, etc. This is to kill the interrupt. Okay, this is not important. And in case if your CPU is really very slow, temporary buffer is overflow, the hardware will tell you you are too slow, you have lost some data. Basically, it's telling you something like that. All right. Okay, that's all for this lecture. So now you see with this super microcontroller, you are able to digitize input from A or 12 sensor. But this one is very, very powerful. This is why make you feel very, very complex, etc. Okay, it's like what I say. Actually, what you need at your level, you just need to you want to have a bicycle, but with the price of bicycle, you get a sport car. That is the situation. But you consider this as a bonus lah. All right, I guess in real life, it will be good lah. Okay, if you pay a price of a bicycle, you get a sport car. Why not? Right? So you must consider this as an advantage. All right. Okay, we take a short break of 5 minutes. Then we start at 4:55. All right.